Okay, if there are no questions, let me proceed with our last synchronous session for this semester. Tuwa-tuwa siguro kayo, no? Last na. Okay. So this is the second part of my presentation on transformers. Just as a review, okay, we studied the ideal transformer last Tuesday. And this is your typical scenario. Okay, your transformer consists of a primary where the source is connected and a secondary where the load is connected. And if you take a look at the transformer equations in the phasor domain, E1 over E2, this is the primary voltage, phasor voltage over the secondary phasor voltage is just equal to N1 over N2, which is the turns ratio of the transformer. Then I1 over I2 is equal to the reciprocal of the turns ratio that's equal to N2 over N1. That's the first and most important relationship for the transformer. Okay. And then we said that from the point of view of your source, what it sees, in other words, the equivalent of this entire circuit is really just an equivalent impedance. And that equivalent impedance is equal to N1 over N2 squared multiplied by Z of L. In other words, if I get this impedance, I multiply it by the square of the turns ratio, I effectively refer this impedance to the primary side. In other words, you can get rid of the transformer and then just place that particular impedance here directly across the source. And then the other thing that we studied was that the power and reactive power delivered to the primary will be the power and reactive power delivered by the secondary. In other words, the transformer will just pass on whatever power and reactive power it receives. It will not take any of it. Kumbaga, wala siyang cut, wala siyang kinukupit dun sa power at saka reactive power na pinapadala sa kanya ng source. No? Lahat nito, pinapasa niya uli dun sa load. Okay. Are there any questions with regard to these three important relationships? Actually, four, no? Four important relationships. Any questions? Okay, thanks. Okay, so let's move on to some more examples. So this is the fifth example that I'm going to be giving. Okay, let me just read it. The circuit shown represents the situation where a load is far from its source. I have a load here, and it's far from the source, such that the line connecting the source to the load is very long. Typically, the impedance of the line is negligible, but when the line is very long, then we have to take into consideration the impedance of the transmission line. Now, ZF represents the lumped impedance of the transmission line or the feeder wire. So sometimes you call it transmission line, sometimes you call it a feeder wire that connect the source to the load. Now we will assume that the load draws 10 kilowatts at 0.9 power factor lag at a voltage of 220 volts RMS. In other words, the source voltage was adjusted so the 220 volts appears across the load. The source voltage would have to be a little bit higher or higher than 220 volts because there's going to be a voltage drop across your feeder line. So expect this to be higher than 220 to be able to accommodate the voltage drop here. Okay, so the problem is determine the RMS value of the source voltage and the power and reactive power supplied by the source. Okay, I'm not going to write out the solution as I usually do. I already have all the solutions in my slides, and this is in the interest of time so that I can present more to you today. So what is the solution? Okay, so this is our system. From the power triangle, I'm able to compute for the reactive power that is delivered to the load. So this is my power triangle. P is equal to 10,000, 10 kilowatts. The power factor is 0.9. Therefore, this angle is the arc cosine of 0.9. So we know that the tangent of that angle is Q over P. So Q is equal to P times the tangent of the arc cosine of 0.9. And we get 4843.2 volt amperes reactive. From that, I can compute the volt amperes of my load, no? Or the apparent power of the apparent power of the load, or the volt amperes of my load. That is SL. Okay. SL, which is actually the magnitude of your voltage multiplied by the magnitude of your current, is just piece of L divided by your power factor. Remember, no? Your power factor is defined as the ratio of real power to apparent power. So if I want to get the apparent power, that's just PL divided by my power factor. So this is my apparent power, or the volt amperes of my load. Okay, there are many ways of solving the problem. Now, again, what are we being asked for here? We're being asked for the RMS value of the source voltage and the power and reactive power supplied by the source. So there are many solutions to the problem. The first solution that I'm going to suggest is a phasor-based approach, which is probably the approach that you will do immediately, that you're inclined to do immediately. So this is using phasors. Okay, let VL be our reference phasor. In other words, we assign the phase angle 0 to VL. As I mentioned earlier, we can do this to any particular voltage in your circuit if there are no angles specified for any of the voltages in the circuit, voltages or currents in the circuit. So let VL be our reference phasor. That's 220 at an angle 0 degrees. I can compute for the phasor current I of S from the complex power formula. I know that the complex power delivered to the load, which is VL multiplied by I of S conjugate, is equal to P of L plus J Qs of L. And I already computed 4 Qs of L. Na-compute ko na yung value ng Qs of L in the previous slide, no? which is 4843 volt amperes reactive ito. So from this formula, from the complex power formula, I can compute for the conjugate of the current that flows through the load. Okay, and that's just P plus JQ, PL plus JQL divided by P of L. No? Meaning to say that's 50.51 at an angle minus 25.84 degrees amperes. Therefore, I of S will be the conjugate of this, which is 50.51 at an angle 25.84 degrees amperes. Okay, any questions so far? Okay, so if nobody shouts out anything or nobody tries to get my attention, I'll assume no, walang tanong. No? Okay, so knowing I of S, any suggestion on what the next step should be? Anyone? Shout out lang. So ano yung alam ko na, no? Maybe I should go back to this. So alam ko na tong I of S. Okay? So I know V of L. No, this is my reference phasor. So what do you suggest would be the next thing we do? Anyone? Pa-shout out na lang, no?
Find the voltage drop across the feeder line.
Yes, you can do that, no? You can find the voltage drop across the feeder line. Bakit natin gusto malaman yung voltage drop, Rick?
So that we can use KVL and find the voltage of the source.
Okay, exactly. No? Exactly. So from KVL, I can now apply KVL, no? The voltage at the source is the voltage drop across the feeder line plus the voltage across the load. So in effect, pindot lang ng calculator to, no? I know all of these quantities. Right? So this is my current This is the feeder impedance, and then this is the voltage across my load. So I'm going to get 238.1 at an angle 2.23 degrees volts. Okay, so yung isang tanong ng problem, what is the RMS value of the source voltage? Ano ngayon yung RMS value ng source voltage? Can I hear from someone else? Isa-isahin ko na lang kayo, no? Si John. What is the RMS value of the source voltage, John? John Edric?
336.6 po.
Ano uli yun? What did you say?
336.6 volts po.
No. I'm talking about RMS value, no? I think what you did was
Ay.
you kinompute mo yung ano, no? Yung peak, yung amplitude, no? Actually, nandito na siya, no? This is already the RMS value of your source voltage, 238.1. No? That's, remember that in the phasor domain, our magnitudes are actually already the RMS value. Okay, so now how do we get the power and reactive power delivered by the source? Any suggestion, Justin? Si Justin Bryan. Paano natin kukunin yung power and reactive power delivered by the source?
Sir, pwedeng mag-complex power.
Yeah, complex power, right, no? Kasi alam ko ngayon yung voltage at the source in phasor form. I know the current through the source in phasor form, so applying ko lang ng complex power. Right? So the complex power delivered by the source is V of S times I of S conjugate. So I'm going to get this. So right away, yung P of S, alam ko, is 10612.2 watts. And then 5659.5 vars yung Q of S. So andun na lahat ng sagot na kailangan ko, no? The power delivered by the source is 10612.2 watts. The reactive power delivered by the source is 5659.5 vars. And the RMS voltage of the source is 238.1 volts. Okay. Any questions? Very, very straightforward. So this is one approach. Okay, this is an alternative solution using power balancing. So it's good for you to know how to use either approach. Sometimes one approach is easier than the other approach. Okay, alam ko na to, no? This we already figured out earlier from the power triangle. This is Q of L, and then this is S of L. Knowing S of L, I can immediately compute for the RMS value of the current I of S. Right? Because S is equal to V times I. S is equal to the RMS value of voltage multiplied by the RMS value of current. So knowing S of L, I of S, mako-compute ko kaagad. Kasi alam ko naman yung V of L, no? V of L is just 220. Right? Thus, I of S, we're only looking at the RMS value is 50.51 amperes. If we compare this to what we got earlier, yes, no, it's the same. Except that earlier, we computed for it as a phasor. So dito, kinompute natin as 50.51 at an angle minus 25.84. But dito, we're only interested in the RMS value, so that's just 50.51 amperes. Okay, now, we can get the power and reactive power supplied by the source using power balancing. The power supplied by the source is the power absorbed by the feeder line plus the power absorbed by the load. Okay. The power absorbed by the feeder line is just I of S squared times the resistance of the feeder line. The resistance of the feeder line is 0.24. So, asan yan dito? Ito, no? 0.24. That's the resistance of the feeder line. So let me go ahead. Okay, and then the power absorbed by the load is 10 kilowatts or 10,000 watts. So right away, I can compute for the power delivered by the source. And then you have a similar way of computing for the reactive power delivered by the source. That's the reactive power delivered to the feeder line plus the reactive power delivered to the load. So delivered to the feeder line, that's IS squared times X of the feeder line, the reactance of the feeder line, plus Q's of L, which is what we computed up here, 4843.2 VARs. So I'm going to get 5659.5 VARs. So ang unang nasagot natin dito is the power and reactive power delivered by the source. So what is the second thing that we have to compute for? We have to compute for the voltage delivered by the source. How do I do that? I can get the apparent power delivered by the source using the power triangle. So using the power triangle, I know P, I know Q, I can get S. S is just the square root of P squared plus Q squared. So I get 12,027 volt amperes. But I know that S is equal to voltage times current. And I know my current. My current is here, 50.51. Therefore, my voltage is just 12,027 divided by 50.51, and I'm going to get 238.1 volts. So those are exactly the same values. Those are exactly the same values that we computed for when we use the phasor method. And note that in this method, I did not have to use any complex numbers whatsoever. All of the numbers that I used here are real numbers, no complex numbers. The same answer. Okay, so do you see the difference between the two solutions? Okay, let me ask you, ano yung mas gusto nyo? The first method or the second method? I just want to poll you. Those that like the first method more, can you give me a thumbs up? Okay, so some people prefer the first method. Like I said, tendency of students in particular is to use the first method because I guess they're more comfortable with circuit analysis techniques rather than power balancing techniques. But actually, when you go to industry, it's really the second method that is more applicable. So any question with regard to this? Okay, this is what I want to do. This is exactly the same load, 10 kilowatts, 0.9 power factor lag, 220 volts, the same load voltage, the same power factor, the same real power. And this is exactly the same source. Well, not exactly the same source, This is the source that is needed to supply this load. But what I'm going to do is, okay, this is the same feeder line, exactly the same feeder line. Sorry. Exactly the same feeder, again, exactly the same feeder line, exactly the same load. Okay. What I'm going to do is I'm going to insert two transformers. This transformer is a step-up transformer, and this transformer is a step-down transformer. The two transformers are going to be identical with a voltage ratio 230 volts to 7967 volts. If you ask me, why this voltages? Well, this appears to be a standard transformer, kaya siya yung ginamit sa example. So you will find this type of transformer, I guess, in industry. So the question is the same. determine the RMS value of the source voltage and the power and reactive power supplied by the source. But the scenario is the same as the previous question. No? The load is far from the source, and the difference now is that we have two transformers, one step up and one step down. Okay, this time I'm going to use a power balancing solution. You can solve this using the phasor method. You can try that as an exercise, but I just want to solve this using power balancing, just to give you more examples of power balancing. From the previous example, from example 5, I already computed for I of L, which is 50.51. From the current relationship in transformer 2, I can compute for the current in the feeder line. I of F is equal to N1 over N2 times I of L. Let's look here. No? Ito, I of F, sorry. I of F is going to be N1 over N2 multiplied by I of L. That is just from the current relationship in a transformer. So I'm going to compute for I of F, and that's now 1.46 amperes. Without the transformer, the feeder line current would have been 50.51, but because of the transformer, the feeder line current is now just 1.46 amperes. Okay, what is the power and reactive power now supplied by the source? The power and reactive power supplied by the source, remember that the transformers are ideal. They do not consume any power and reactive power. They only pass this on. So the power and reactive power supplied by the source would be that supplied to the feeder line plus that supplied to the load. And notice now that that is going to be 10,000.5 watts and 4843.9 var. So significantly reduced from that of example 5. Why was it significantly reduced? Because we were able to reduce I of F. We were able to reduce the feeder line current. Originally, it was the same as the load current, but because of the transformer, okay, it is now reduced. Okay, the apparent power delivered by the source is just the square root of the power squared plus the reactive power squared. And I'm going to get this, no? 11,111.8 volt amperes. Okay. Now, I of S, the current delivered by the source, I can get from the current relationship of transformer 1. I of S is just N2 over N1 times I of F. And in fact, I of S is just going to be translated back to what it was originally, which was 50.51 if we did not have any transformer 2. So now I know I of S, I know S of S, I can compute for V of S. V of S is S of S over I of S, and I get 220.03 volts. So here are the three answers to the question. This is the real power delivered to the load, delivered by the source rather. This is the reactive power delivered by the source, and this is the voltage that is required across the source. Any question with regard to the solution? Any question? So far, okay? Nasundan niyo? Okay, let me compare example 5 and example 6. So I'm comparing it with respect to load power, the same load power. In other words, the load experiences exactly the same thing in terms of power, reactive power, And of course, load voltage. No? The load voltage is the same for example 5 and example 6. In other words, from the perspective of the load, exactly the same work can be done. Okay, for example 5, our feeder current was 50.51. In example 6, we brought this down to 1.46. So in example 5, this is what was lost in the feeder. 612.2 watts. Now in example 6, ang laki ng binagsak nung nawawala sa feeder. 0.51 watts na lang. Same thing with the reactive power. In example 5, this is what was lost. Example 6, that dropped significantly, very, very significantly to 0.68 VARs. So that now, the power delivered by the source from being 10,612 is just now a little over 10,000. And the reactive power delivered by the source from being 5659.5 is just now a little over 4,843. In other words, if you take a look at these two, the power delivered by the source and the reactive power delivered by the source, it's almost equal to the load power and the load reactive power. And if we take a look at the source voltage, in example 5, in order to have 220 volts across the load, I had to have a source voltage of 238 volts. Whereas in example 6, in order to have 220 volts across the load, I only had to increase my source voltage by 0.03 volts. Okay. So what are we saying here? Inserting the two transformers made the system much more economical to operate. It made the system much more economical to operate. It seems counterintuitive. No? Nung wala yung dalawang transformer, ang laki ng losses natin. No? Nagkabit tayo ng transformer, so we expect the transformer will introduce some losses, but actually if it's an ideal transformer, it won't introduce any losses. And now it's much cheaper to operate the system. And that's exactly what distribution companies do. The line losses are reduced by inserting transformers in the system. I think you already know that sa labas ng mga bahay ninyo, sa poste ng Meralco, may transformer ron. The purpose of that transformer is to reduce the voltage from the distribution voltage down to 220 or 230 volts. Okay. The reason it does that is to reduce the line losses. And this is the reason why AC won over DC in the distribution of electric power toward the end of the 18th century. There was some politics going on there. In fact, I think there was a movie made of this quite relatively recently. See, Thomas Edison was a proponent of DC. He wanted everything to be DC. On the other hand, ano ang pangalan nito? Don, you might remember the name, no? Yeah, that's right, no? Sabi ni Rick, si Tesla, no? Si Tesla was a proponent of AC. And the reason why AC was being pushed by Tesla was because of this, ano, na you could actually reduce the line losses by just jacking up the voltage. No? The higher the voltage, the same power, the less the current, the less the losses in your line, your I squared R losses and your I squared X losses. But the problem at that time was most of the machinery run using DC. And it was Tesla also that discovered that invented, I guess, the induction motor, which actually revolutionized AC machinery at that time. So eventually, AC won over DC. So these are just some examples of transformers used in power distribution. This is the power substation, where you step up and then eventually again step down voltages at very, very high, will step up to very, very high levels. And these are the really long haul lines. For example, the line that will connect your generator, for example, in the provinces in northern Luzon to Metro Manila, ito, no? You can go up to 500,000 kilovolts voltage. That would be your high voltage side. No? Your low voltage side would be about 115,000 kilovolts or 69,000, 115 kilovolts or 69 kilovolts, no? From 500 kilovolts or 500,000 volts. And then the distribution side from 69 kilovolts to 13.8 kilovolts. So this is immediately before reaching the transformers outside of your homes. And then outside of your homes, that's from 13,800 volts to, actually, ang Meralco is 230 volts. No? I think it's 230, not 220 volts. So that is why electric power is distributed that way to reduce losses. Any question with regard to that? Okay, so again, another example. Find V sub S and the power and reactive power supplied by the source. Assume the transformers are ideal. Okay, so in this particular situation, we actually have 3 feeder lines. You have a load, you have a transformer, and then there's a feeder line between transformer 2 and the load. No? And the feeder impedance is J3. And then here, you have another transformer, and then connecting transformer 1 and transformer 2, you have another feeder line whose impedance is J2. And finally, connecting the source and transformer 1, we have another feeder line whose impedance is J1. Okay, so the problem is find V sub S, okay, and the power and reactive power supplied by V sub S. We assume that V sub S is adjusted so that you get 220 volts across your load. Okay, this time your 2 transformers are not identical. No? Ang turns ratio nito is 1:2, and the turns ratio of this is 4:1. T1 is a step up, and T2 is a step down. Okay, so again, I'll present many solutions here. The first is using a phasor-based approach. Phasor-based approach. Let's just try to outline yung phasor-based solution. No? Outline lang natin. Okay, so alam ko yung gagawin ko tong reference phasor, V sub L. Right? So that's my reference phasor. So V sub L will be 220 at an angle 0 degrees. I know P from the power triangle. I can compute Q. Okay. If I know Q, then I can determine I sub L using the complex power formula. If I know I sub L, I can get the voltage drop across J3, and that will allow me to determine E4 using KVL. No? E4 is just I sub L multiplied by J3 plus V sub L. If I know E4, because of the turns ratio, I can compute for E3. And if I know IL, I can compute for I sub X also from the turns ratio. So pwede na naman ako mag-KVL dito. No? E sub 2 is equal to I sub X multiplied by J sub 2 plus E sub 3. If I know E sub 2, I can compute for E1 from the transformer characteristics. If I know I sub X, I can compute for I sub S, and then pwede uli ako mag-KVL dito to determine V sub S. If I know V sub S and I know I sub S, I can use the complex power formula to determine P sub S and Q sub S. Were you able to follow the process? Nasundan ba yung sinabi ko? Did I go too fast? Let me hear from the others. No, I hear the same people. Sino po bang? I want to know from si Chanel, si Eric, si Joseph, si Joyce. Nasundan ba nyo? Okay, thank you. No, thank you for the feedback. Okay, so yun yung proseso. No, so I will just skim through the solution now. No, so this is to determine I of L. Because I computed from the power triangle P and Q. So now I apply the complex power formula to compute for I of L conjugate. And from I of L conjugate, I get I of L. And then now this is my KVL. E sub 4 is I of L J3 plus V sub L. And this allows me to compute for E sub 4. If I know E sub 4, this is the secondary voltage at transformer 2. I can compute for the primary voltage at transformer 2, no? Because E3 over E4 is equal to 4 over 1. No? And I'm going to get E3 is 916.09 at 1.16 degrees volts. Remember that the transformer primary and secondary will always be in phase. So kung ang angle nito is 1.16, ang angle nito will also be 1.16. And then I can also compute for I of X. Using the formula, I of X over I of L is equal now to N2 over N1, no? Not N1 over N2. And I of X will now be 5.05 at the same angle as I of L, minus 25.84 degrees. Okay, just a tip, no? Just so that you can audit your answers as you make your computations. Kapag mas madaming turns, mas malaki yung voltage, pero mas maliit yung current. Okay? In other words, if you're going from a smaller number of turns to a higher number of turns, the voltage will increase, but the current will decrease. In this case, this is a step down. So you're going from a lower now. Yeah, that's right. No, you're going from a lower number of turns to a higher number of turns. No, kasi step down siya. No, so step down. So here you have lower number of turns. Here you have a higher number of turns. So the voltage will increase, but the current will decrease. Now, when you're going from a higher number of turns to a lower number of turns, your voltage will decrease, but your current will increase. So that's the way you should also audit your answers in your head. Okay, so alam ko na yung E3, alam ko na yung IX. I can do my second KVL, which will make me compute for E2. And then using again the transformer characteristics, I can compute now for E1 and IS using the turns ratio of T1. Alam ko yung E1, alam ko yung IS, I can now compute for VS. So ito yung unang hinihingi. No? The RMS value of your source voltage is 495.1. Okay. And then P of S and Q of S can be determined from the complex power formula. That is, the complex power delivered by the source is your voltage multiplied by your current conjugate. So you're going to come up with this in rectangular form. So alam natin that this is P and that this is Q. Any question? So my advice to you when you see the problem is you try to formulate a strategy of solving it already in your head before even turning on your calculator. Try to formulate a solution in your head or a plan of attack in your head, such as what we did before we actually computed for anything. Any question? Okay, here is another solution. And what we can do here, so I'm going to present to you another solution. And what we do here is successively referring quantities from the rightmost side to the leftmost side. So now what relationship are we going to use? We're going to use Z equivalent is equal to N1 over N2 squared times Z of L. So we'll start with Z3 prime and VL prime. Z3 prime and VL prime will be Z3 and VL referred to the primary of the second transformer. So Z3 prime is equal to your turns ratio squared multiplied by Z3. VL prime, this is just now the turns ratio of your transformer. VL prime over VL is equal to 4 over 1. No? So VL prime will be 880 at an angle 0 degrees. So this is now my equivalent circuit. I removed the transformer here, and this is the equivalent circuit that is seen at the primary terminals of the second transformer. So all I did was referred the quantities from the secondary to the primary. Now the load, the power and the power factor and the reactive power of the load will be exactly the same. Because remember what we said about the transformer, kung ano man yung power na nakukuha niya, yun din yung power na binibigay niya. So hindi magbabago yung power at reactive power at power factor ng load. Ang magbabago lang is yung voltage. And that voltage now is 880 from 220 because my turns ratio is 4:1. So na-multiply by 4. Okay, ngayon, itong lahat ng quantities na to, pwede ngayon nating i-refer dito sa primary, So that's what we're going to do next. You let Z2 prime, Z3 double prime, and VL double prime be Z2, Z3 prime, and VL prime referred to the primary of T1. So this is now Z2 prime. Okay. This will be my Z3 double prime. And then this is now my VL double prime. And finally, I just have this equivalent circuit. For the load, di naman nagbago yung power at reactive power ng load. Ano? The power and reactive power of the load will not change. It's still the same. This is something we computed earlier from the power triangle. No? Ang magbabago is yung voltage. I can compute for the conjugate of the source current by dividing the complex power by my load voltage. So this is just a complex power formula. No? So this is going to be the conjugate, remember, the conjugate of my source current. So my source current is just going to have the negative of the angle. No? So 10.10 at an angle minus 25.84 degrees amperes. On the other hand, my KVL now is V of S is Z1 plus Z2 prime plus Z3 double prime multiplied by I of S plus V of L. So I'm going to come up with this. Okay, and the complex power delivered by the source is just Vs multiplied by Is conjugate. And I'm going to get exactly the same answers that I got earlier. Any question? Any question? Still another solution. Use power balancing. Kanina sabi ninyo, most of you said earlier that you like the phasor solution the best. Um, and I don't blame you, no, because your inclination would really be to use the phasor solution. But actually, like I said, a lot of times power balancing is the easiest way to do things. Okay. I can get from S of L, no? From the apparent power delivered to the load, I can get the magnitude of my load current. The way we computed this earlier was through complex power. But actually, if I'm just interested in the magnitude, I don't have to use the complex power formula. I just get the apparent power and I deliver it by the voltage across the load, no? And I'm going to get the RMS value of my load current. Now, from the transformer turns ratio, I can solve for Is of X and Is of S using the turns ratio of T2 and T1. So this is Is of X, 5.05 amperes, and I'm only dealing now with RMS value. Then Is of S is Is of X, then the turns ratio of T1, which is 10.10 amperes. Actually, these are the same quantities we got earlier, except that earlier we got the phasor quantities. So here we're getting just the RMS value. And then take a look at this, no? What is the power and reactive power delivered by the source? The power delivered by the source is just the power delivered to absorbed by feeder line 1 plus the power absorbed by feeder line 2 plus the power absorbed by feeder line 3 plus the power delivered to the load. So what is that? That is Is squared. No, we're talking about the source. Is squared times R1. This is the feeder connected to the source. And then Ix squared R2. R2 is the feeder between transformer 1 and transformer 2. And then IL squared R3. R3 is the feeder between transformer 2 and the load. Finally, the power delivered to the load. Okay, and you're going to get 4,400.47, which is exactly the same figure we earlier computed. And you do the same thing for Qs of S. So finally, to solve for V's of S, we get the apparent power delivered by the source, which is the square root of P of S squared plus Qs of S squared. We divide that by the RMS value of the source current, and we get 495.1, which are exactly the same answers we got from solution 1 and solution 2. So three possible solutions. And I maintain that itong third solution is the shortest. Are there any questions? Ang isa pa maganda sa third solution, I don't deal with complex numbers anywhere. Lahat ng mga numbers dito are real numbers. Any questions? Okay, because I'm going to move to a slightly different topic now. So other uses of transformers. So in all the problems that I've shown you so far, in all the examples that I've shown you so far, the use of the transformer is as a power distribution component. No? But there are actually other uses of transformers. For example, in electronic circuits, if you take a look at a PCB printed circuit board, for example, ito, no? This is actually a power supply. No? You find a transformer here, and you find a transformer here. So there are uses of transformers in electronics. For example, you use transformers in impedance matching. You use transformers to filter out DC signals. Remember that a transformer, uh, in a transformer, a voltage is only induced in the secondary if there is a changing flux with time. So kung DC, there's no changing flux with time, there's no voltage induced. Now, if you have a signal that is composed of a DC component and an AC component, yung DC component hindi lulusot, pero yung AC component lulusot. So it's also a filter. No? It's a DC. It filters out DC, yung transformer. So you see a lot of other uses of transformers. I want to touch on impedance matching for maximum power transfer. This is quite important. Consider this circuit shown, where this is your load. This is your load. And then this is like the Thevenin equivalent. Okay, of a circuit, no? Of a circuit. Or it can be your source. Thevenin equivalent of a circuit, or it can be your source. You remember the condition for maximum power transfer? If you want maximum power transfer to be delivered to this load, then this load must have the same resistance as the Thevenin resistance or the source resistance for maximum power to be delivered. Naalala ba niyo yan? Or nakalimutan na niyo? That was taken up first module. No, first it was the subject matter of the first long exam. Okay, what if meron akong load na hindi ko ma-adjust yung value, no? Ito, that's already given, ano? That's the Thevenin resistance of your circuit or your source resistance. And then what if I have a load that I cannot adjust this value? How do I deliver maximum power through it? What you do is you use what is called a matching transformer. So between the load, and your circuit, you insert a transformer. Of course, the assumption here is that the source is AC. It is not DC. Otherwise, your transformer won't work. You use a matching transformer. In the primary side, RL is seen by the source as this. So this is referring the secondary to the primary. Ang nakikita ng primary is your load resistance multiplied by your turns ratio squared. This is referring Rs of L to the primary. Now what you want to do is, you want to adjust N1 over N2 so that itong RL prime will now be equal to Rs. And that's what you call impedance matching. So this is a simple example. The output stage of an audio amplifier has an output resistance of 2 kilo ohms. Okay, so meron akong audio amplifier. Ikakabit ko dapat yung speaker doon, no? To my audio amplifier. Unfortunately, the output resistance of this amplifier is very high. It's 2 kilo ohms. Kapag nagkabit ako ng 6 ohm speaker sa kanya, I'm not going to get maximum power delivered to my speaker. So what can I do? I can apply a matching transformer. Now let's say the transformer has 400 turns in the primary. How many turns must its secondary have? So this is my load resistance. This is my source resistance or my Thevenin resistance. What I want is RL prime is equal to Rs of S. So RL prime is N1 over N2 squared multiplied by RL. I want that to be equal to 2000. And I know that N1 is 400. So all I have to do is compute for N2. So if I have a transformer with 22 turns, approximately 22 turns in the secondary, 400 turns in the primary, then this amplifier now will deliver maximum power to this speaker. Are there any questions? So this is a very practical application of the transformer. So there's a question. Can you just ask your question directly, Rick?
Do we always round up the number of turns?
Well, mahirap naman pag nagwawain ka ng transformer na eksaktuhin mo 21.9, ano? So you have to be practical. So gawin mo na lang 22, no?
Pero yung pag-round po, round up po ba palagi?
Actually, not necessarily, no? Not necessarily.
Okay, thank you.
Okay. Okay, the last topic that I want to discuss is practical transformers. So far, ang discussion natin has been confined to ideal transformers. But we all know that in the real world, there's no such thing as something being ideal. Ang assumption natin dun sa ideal transformer are both coils have zero resistance. Sa ideal, no? Both coils have zero resistance. But we know that a transformer is made up of a winding that's a long piece of wire, and that wire will have some resistance, although resistance is small. And then we also know that a leakage flux will exist in both coils. No? So the ideal transformer, we assume whatever flux generated at the source side will confine itself to the core being very low reluctance. But actually, that's not the case. No? There's going to be some flux that will leak this way. No? Meron kang flux na ganito. So you call this leakage flux. In fact, even between coils, no? Let's say this is my core, even between coils, dito pwede ka rin magkaroon ng mga leakage flux. No? You can also have leakage between winds. Between winds, you can have leakage. And then the third assumption was that the core was lossless. But actually, there's a resistance loss in the core. What do you mean by resistance loss? Actually, the flux that flows in your core causes what is called currents, eddy currents. Ang tawag niya is eddy currents to flow in the core material. These currents are circular currents, no? So if your flux is flowing, for example, here left to right, meron kang currents na paikot flowing around the core, no? You call those eddy currents. That's why eddy kasi paikot-ikot siya. No? In fact, the way they reduce that is they make the core what is called laminated. Pag tinignan mo yung core ng transformer, it's not a solid piece of metal, but it's actually laminated pieces of metal together so that you reduce your eddy currents. Eddy currents, by the way, is also the principle of your induction heater or your induction stoves. Some of you, well, I don't have one in my house, ano, but some of you, yung mga kalan ninyo sa bahay, baka induction na. No? Imbis na you have heater coils, you have induction coils. And ang ginagawa nito mga induction heaters na to, ginagawang core yung pinakalutuan mo, no? Your pot, your cooking pot or your cooking pan is made a core. And it creates eddy currents to flow in your pot, and that causes your pot to heat up. Yun yung principle ng induction heaters. So that's what's happening here in the core. No? Nagkakaroon ka ng parang resistance loss. So that when you touch the core, medyo mainit siya. And finally, the permeability of the core is not high, is high. So this is a high permeability. Permeability is analogous to conductivity when it comes to magnetic flux. It is high, but it is not infinite. Therefore, you need a certain excitation current. A part of I1 is needed to cause the flux to flow. In other words, not all of I1 will come out here in I2, no? Or will contribute to the flow of I2. Part of it will contribute to the flow of the flux. So these are the four characteristics that we have to take into account in a practical transformer. And this is how we model the practical transformer. R1 and X1, this is the winding resistance and the leakage reactance of coil 1. R2 and X2, this is the winding resistance and the leakage reactance of coil 2. And then itong R sub C, this represents the core resistance. So this is what I was talking about earlier. No? This is the inclination of the core to resist the flow of eddy currents. And then X of M takes into account the component of I1 that is needed to magnetize the core. No? So may itong I1, hindi lahat papasok dito. May component siya rito to magnetize the core. No? That is your excitation current. And then in the middle of this is an ideal transformer. Okay? So your transformer, this is actually your transformer. No? Ang transformer mo is this. This is your transformer. But you can only apply the ideal transformer equations to this middle part. In other words, I cannot say that V1 over V2 is N1 over N2. Hindi ko na pwedeng sabihin yon, no? I cannot say that I1 over I2 is N2 over N1 because that will only now apply to this central portion. Now, in many cases, we can neglect your core resistance and your magnetizing component, the magnetizing component of your core. So that itong IEX, your excitation current, your core excitation current is negligible. Sometimes we just, in the nameplate, you just see there a fixed core loss in the nameplate. So pag tinignan nyo yung nameplate ng transformer, makikita na lang ninyo at full load, the core loss is, sabihin natin, 20 watts. Yun ang makikita ninyo. So if we take out RC and X of M, so tinanggal natin yan dito. By the way, no, that could have been referred to the primary or could have been referred to the secondary. No? Going back to this thing is referred to the primary, but it could have been actually referred to the secondary. So we take that out. This is what is left. No? This is still my transformer. Ito pa rin yung transformer ko. Now, with respect to the ideal transformer, E1 over E2 is equal to N1 over N2, and I1 over I2 is equal to N2 over N1. That's with respect to this center part. Okay, so the voltage equation applies to E1 and E2, not to V1 and V2. It's possible to refer all impedances to the primary side. So itong impedance na to, i-refer natin dito sa primary, and then this voltage we also refer to the primary. No? So you're going to get this equivalent circuit. No? Pinapakita lang dito is yung primary side. Okay. So your I1 is just 1 over 8 times I2. Okay. And then this is your V2 referred to the primary, no? 8 times V2. And R equivalent and X equivalent now is the total of your primary impedance plus the secondary impedance, no? The coil 1 impedance plus the referred coil 2 impedance. Okay? So these are your formulas. R equivalent is R1 plus A squared R2, and X equivalent is X1 plus A squared times X2. So here's an example. This is my last example. A single phase transformer has the following nameplate ratings. This is your volt amperes. This is your voltage rating. This is high voltage side and low voltage side. So it does not specify primary or secondary, just high voltage side and low voltage side. And the equivalent impedance is referred to the low voltage side. So the transformer supplies 30 kilowatts at 0.85 power factor lag to a load whose voltage is 225 volts. So the load is obviously connected to the load voltage side, no? Because the high voltage side is rated at 7620. The load is at 225 volts. Obviously, that's connected to the low voltage side. So find the input voltage, the power and reactive power supplied by the source, and the efficiency of the system. So I'm introducing here a new term, efficiency. Later on, we'll define what efficiency is. So this is actually my equivalent circuit. This is my transformer. My turns ratio is 7620 to 230. This is the equivalent impedance of the transformer referred to the low voltage side. Ito referred to the low voltage side. Sorry, there's an error here. No? Wala itong 0.5. No? Dapat wala yan. There's an error there. That 0.03 plus J.04 ohms. Okay, so this is the specified load where your voltage is 225 volts. So there are several solutions. For example, you can use power balancing with VS referred to the low voltage side. So power balancing, where ito, I will refer this to this side, no? To the low voltage side. So this is going to be VS prime. The equivalent circuit with VS referred to the low voltage side. From the load power triangle, I can compute for Q and for S. Q, first I compute for Q. I can compute for S, which is equal to P over power factor. And then I can compute for the magnitude of I, which is just S divided by V. And then the power and reactive power supplied by the source will just be now IL squared R equivalent plus PL and IL squared X equivalent plus QL. So ito na yung isang sagot na, yung dalawang sagot na hinihingin ng problem. What is efficiency? Efficiency is the power delivered to the load divided by the overall power or the total power supplied by the source. The power delivered to the load divided by the total power supplied by the source. So the power delivered to the load is 30 kilowatts. The total power supplied by the source is 30.738 kilowatts. So I have a 97.6% efficiency. Now to get VS prime, I just get S of S, which is the square root of P plus Q, P squared plus Q squared. And then I divide that by Is of L. So this is VS prime. But I have to refer that back now to the high voltage side because that was applied at the high voltage side. So I apply the turns ratio. So my actual power supplied at the high voltage side is 7,696 volts. So those are the three answers I was looking for. 4 answers rather I was looking for. Power supplied by the source, reactive power supplied by the source, the efficiency, and the source voltage. Okay, so I won't go through this anymore with so much detail, no? But I could have used a phasor-based approach with J equivalent and the load referred to the high voltage side now. Kasi kanina, we referred the source voltage to the low voltage side. Now we will do the opposite. We're going to refer J equivalent and the load to the high voltage side. No? In effect, ito yung magiging circuit natin. No? So we retain this, and then this is referred from the secondary, and this is also referred from the secondary. And then you can use your phasor method to compute for your I's of S using your complex power formula, and then B's of S using KVL. Okay, and then using complex power formula to determine P's of S and Q's of S. And finally, your efficiency, which is the power delivered to the load over the total power supplied by the source. And that ends EEE123 lectures for you. Any questions? I hope I did not go too fast.
Sir, yung question po about yung power balancing solution. What if
Yes,
po
yes.
hinihingi yung angle nung kunwari voltage, applicable pa rin po ba yung gumamit ng power balancing?
What in particular?
Hinihingi po yung phi ng voltage source.
Hinihingi yung angle.
Apa.
Okay, in general ganito 'yon, ano? If you need to solve for phasor quantities or angles, then go to the phasor method. Okay? But that does not mean that I cannot get the angles from the power balancing equations, no? Because let's tignan natin yung power balancing, no? Ano bang problem to? Sorry. Okay, kagaya nito, no? What if the problem was to get the phasor value of V's of S, no? Kasi ang problem dito is just to get the RMS value of V's of S, no? What if the problem is to get the phasor value of V's of S? I can get the power factor of V's of S because I know P's of S and Q's of S. So I can get the angle, so I can get the power factor. Right? So from the power factor, if I know the phasor value of the current, I can get the angle of the voltage. Nakuha mo yung sinasabi ko?
Apa.
Kasi ito yung S of S, yung sa source, no? A power triangle of the source. So this is P of S, this is Q of S na na-compute ko na itong dalawa, no? So itong angle theta, tangent theta is equal to Q of S over P of S. So makukuha ko yung theta. Now this theta is the difference in angle between your voltage and your current, no? Ano ba yung current natin? Yung current natin dito is I of L. Of course, hindi pa natin alam kung ano yung angle ng I of L, no? But you can determine the angle of I of L from the load. From the load. Dito, no? Kung alam ko yung P of L ay yung Q of L, alam ko yung P of L, right? The load. if I know P's of L, Q's of L, I can get this angle, theta. No? Theta is equal to tangent of, sorry, arctangent of Q's of L over P's of L. Right? That is the power factor. That is actually given na pala yung power factor. Sorry, no? Hindi pala kailangan, no? Alam ko na pala yung power factor dito. So kung ito yung reference ko 225 at an angle 0, if I know the power factor, makukuha ko yung angle nito. I can get the angle of i's of L. If I know the angle of i's of L and I know the power factor of the source, here, the power factor of the, or the angle of the source, I can also get now the angle of V's of S. So pwede. You can use power balancing to get angles. But my suggestion is, kung mga phasor quantities ang hinihingi ng problem, you just do the phasor approach.
Thank you, sir.
Yeah. Usually, ang power balancing ginagamit kapag ang hinihingi lang is yung mga RMS values. Pag hindi ka interesado dun sa angles, just the RMS values. Okay, are there any other questions? So if there are none, as usual, I'm closing this synchronous session. So I just want to say that to those of you that religiously attended these sessions, thank you very much. No, actually, it's also for your own good. And I understand that it would have taken quite a bit of effort on your part, no? But hopefully it pays off for you. No? So that's it. No, I'll stay online until the last person leaves.